Welcome to the debate.
Today, we're diving into something pretty exciting in the LLM space, OpenTSLM. This is a new family of time series language models.
Right, and they're designed specifically to tackle a big blind spot for current LLMs, integrating that, temporal longitudinal data, making it a native input especially for tricky medical reasoning tasks.
Exactly. And the paper digs into how they actually do that bridging. How do you connect a continuous time series signal with the sort of discrete, token-based world of models like Llama or Gemma?
Which brings us to the core tension and our debate today. They propose two main architectural solutions. There's the implicit OpenTSLM-SoftPrompt, or SP, and the explicit OpenTSLM-Flamingo, the FL method.
Yeah. So the big question is, which one of these designs is, well, the better foundation? Which is more robust, more viable for scaling up to handle really complex medical data down the line?
And my stance is pretty clear on this. I believe the explicit approach, the multimodal fusion you get with OpenTSLM, Flamingo using cross-attention, that's the necessary general-purpose architecture if you want real scalability and robust reasoning, especially for long sequences.
See, I'm coming at it a bit differently. While scale is obviously important, I think OpenTSLM-SoftPrompt offers a really compelling advantage in terms of, well, efficiency and simplicity. In situations where you know your sequence length isn't going to be enormous, SP is powerful, parameter efficient, and actually performs better sometimes.
Okay, so let me lay out why I think the explicit Flamingo model is the way forward. The fundamental challenge, as you mentioned, is fusing text and time series. We know that just tokenizing time series values, like text, runs straight into that quadratic cost problem with self-attention. It just doesn't scale. To make time series truly native, you absolutely have to decouple its length from the LLM's fixed context window.
Right.
And the Flamingo approach does exactly that through what they call explicit multimodal fusion. It introduces this quite sophisticated component, the perceiver resampler.
Yeah, that's the core piece for Flamingo, isn't it? Inspired by vision language models, this perceiver resampler, it basically acts as an information bottleneck. It takes all those time series patch embeddings, could be 10 steps, could be 10,000, and it crunches them down into a fixed size latent representation. They call it Z-latent.
Exactly, and that's the absolute key. This Z-latent becomes a dense summary of the signal, crucially independent of the original sequence length L. This compact summary is then fed into the LLM, but only when needed using these gated cross-attention layers. Special tokens like TS basically tell the LLM, okay, now go query that time series summary. The big advantage here is structural, stable memory use.
And you've got the empirical data backing that up, which is pretty persuasive. They showed training Llama 3B on simulated data. And the VRAM for the Flamingo model basically flatlined, what was it, like 60.7 to 61.1 gigabytes? Barely moved, even when the input sequence length L went up by like a factor of 10. That fixed memory footprint, yeah, that's a massive engineering win.
It's more than just a win. I'd argue it's essential for handling real-world clinical data. That fixed cost is precisely why Flamingo shines on the toughest dataset they tested, the ECG-QRT-1. You're talking 12 leads, 10 seconds of ECG data that's complex. And the LLM-3B Flam model got the top F1 score 40.25. Meanwhile, the tokenized baselines, they just crashed, out of memory errors, needing over 100 gigs of VRAM. Flamingo handles the complexity. SoftPrompt couldn't even run the experiment.
Okay. The scaling point for those really extreme long sequences is, yeah, it's undeniable. But let's not dismiss the SoftPrompt approach so quickly. Its design philosophy is all about parameter efficiency, leveraging the LLM you already have as much as possible. OpenTSLM-SP doesn't add those complex cross-attention layers. It's just simpler.
Simpler, maybe, but at what cost?
Well, the simplicity comes from using a fairly small transformer encoder and an MLP projection layer. These map the time series patch embeddings directly into the LLM's hidden space Z, so they effectively look like text tokens to the LLM.
Right. They become sort of pseudo-tokens.
Exactly. And these projected tokens, Z, are just concatenated right into the input sequence alongside the real text tokens. Think like T-pre, Z1, T-desc, Z2. It works like soft prompting. The clever part is that it forces the LLM's own self-attention mechanism to figure out the temporal dependencies implicitly within that single sequence along with the text. It's elegant because it's architecturally minimal. And that minimalism pays off. SP models need very few extra parameters for fine-tuning. You're just doing LoRa on the LLM plus adding that small encoder projector. It's a lightweight adaptation. And we see this translate directly into performance, especially on tasks with shorter sequences.
Which specific tasks are you referring to?
Well, look at TSQA, that's time series question answering, and Sleep-CoT, the sleep staging task. In these cases, the time series segments are naturally shorter, like the standard 30-second EEG windows for sleep staging. And here, the SP models actually did better. The Llama 3.21 BSP hit 97.50 F1 on TSQA and a really strong 69.88 F1 on Sleep-CoT. That beat the Flamingo versions quite clearly in both instances. So if you're dealing with typical sensor data where super long sequences are unlikely, why take on the extra architectural baggage of Flamingo?
You highlight the performance on constrained data, sure, but you're completely skating over the fundamental limitation, that quadratic cost of self-attention. The efficiency you praise is, well, it's fleeting. It vanishes the second your data gets even moderately long or complex.
I'm not skating over it, I'm saying it's a known trade-off.
But it's a killer trade-off. SoftPrompt relies entirely on the LLM's context window. That means memory use grows exponentially with sequence length L and the number of time series N. This isn't just some minor detail. It's the critical bottleneck. Concatenating means you're trying to jam every single time series patch embedding into the LLM's active memory. It's like, I don't know, trying to process 10,000 data points simultaneously through simple attention. The compute requirements just explode non-linearly. It breaks.
I see why you frame it that way, but let me offer a different perspective. Yes, the exponential growth is a constraint, but again, it's an acceptable constraint for specific domains where L is naturally limited. Think about medical staging tasks, like Sleep-CoT. They use short, standardized segments by design. The system never gets near that OM cliff in those applications.
But medicine isn't just short segments.
Of course not, but for these constrained scenarios, SP gives significantly better performance. I mean, look at that Sleep-CoT result again. 69.88 F1 for SP versus 49.33 for Flamingo with the Llama 1B model. That's a 20-point F1 difference. That's huge for a real medical task. That localized performance boost, combined with the lower compute overhead of the simpler SP architecture, makes it the better choice for that niche. We shouldn't force everyone to use an expensive, complex architecture designed for extreme edge cases if it means taking a performance hit elsewhere.
But I argue those aren't just edge cases. They represent the kind of complex, multi-channel data we need to handle in advanced clinical settings. Look at the scaling numbers again. That same Llama 1B SP model, it jumps from needing 4.4 gigabytes of VRAM for the short TSQA task to nearly 65 gigabytes for ECG-QA-COT. And even then, it still crashes, goes OOM, when trying to process a simulated sequence of length 10,000 with just 3 concurrent series. It proves SP is fundamentally a non-starter for complex, multivariate, high-frequency monitoring like multi-lead ECGs. If your medical AI can't handle that kind of data, its clinical utility is severely limited. Flamingo tackles this head-on. SoftPrompt just hits a wall.
Okay, fair point on the wall. But that brings me to my main challenge with the explicit Flamingo approach, the sheer complexity. Implementing it requires quite a bit of engineering overhead, doesn't it? You need that perceiver resampler layer. You need to carefully integrate the gated cross-attention layers every few transformer blocks. You need to train and manage those special TS tokens to signal the input switch. Isn't all that effort a bit, well, over-engineered when the simpler concatenation approach works extremely well and sometimes better on 3 out of their 4 benchmark tasks?
That's an interesting way to put it, though I see it differently. The perceiver resampler isn't just complexity for complexity's sake. It's crucial because the time series is this continuous, high-dimensional beast, while the LLM core is built for discrete text tokens. Shoving every raw patch embedding into the LLM like SMP does is like, imagine trying to read a dense textbook while 100 people are shouting different data points at you simultaneously. The LLM just gets overwhelmed. The resampler acts as that necessary intermediate filter, or maybe a summarizer. It intelligently condenses that massive raw signal down to its core features, represented in that fixed-length Z latent. This architectural choice is what buys you robustness and generalizability. Z latent is a concise digest the text model can query efficiently using cross-attention without drowning in the raw data stream and causing that memory explosion.
So the cross-attention is basically the mechanism allowing the LLM to peek at the time series summary when it needs to without having to hold the entire raw stream in its working memory.
Precisely. It's the sophisticated, and I'd argue necessary, bridge between the continuous signal world and the discrete text world. It's not engineering overkill, it's elegant engineering designed specifically for these kinds of heterogeneous inputs. You're essentially trading a bit of complexity in the interface layer for massive gains in stability and scalability within the core LLM.
Okay, look, regardless of which architecture we prefer, we both absolutely agree that OpenTSLM in either flavor is a huge step forward compared to what came before. We have to remember how badly older methods performed on this stuff.
Absolutely. The paper makes that starkly clear. Text-only LLMs often just fall flat, 0 F1 score, because they can't even generate the right output format or handle the context. Even a massive frontier model like GPT-4o only managed a measly 2.95 F1 on the HAR-CoT test when fed tokenized text. Both OpenTSLM models blew past that, getting up to, 65.44 F1? It shows the power of treating time series as its own modality.
And maybe the most exciting part for actual medical use is the chain of thought, the CoT reasoning. Both SP and FL can generate those free-form rationales before making a prediction. That moves us away from just getting a black box classification label.
Yes, that transparency is critical, especially in medicine. You need trust.
Exactly. And the expert review they did on the ECG-QA rationales from the Flamingo model was really encouraging. The rationales were judged correct or partially correct almost 93% of the time. And crucially, they showed strong clinical context integration, over 85% positive assessment there. So the model isn't just pattern matching, it's explaining itself in a way that makes clinical sense.
That is indeed crucial.
But thinking about that trust and transparency, does the simpler SoftPrompt architecture maybe offer a slight advantage in interpretability? If you're forcing the projected time series token Z directly into the main sequence, couldn't the LLM's standard self-attention weights give you a more direct map of which specific raw time series parts the model focused on, compared to Flamingo, where it's attending to that pre-processed, compressed, Z-latent summary? Is the attention map potentially clearer in SP?
That's an interesting angle.
A potentially more direct attention map. But I'd push back slightly. The high-quality, clinically relevant rationales from Flamingo were generated because the architecture could handle the complex data in the first place. You're suggesting simpler attention might be more trustworthy, but if that simpler SB architecture can't even process the long ECG sequence needed for the task, then the interpretability of its attention map becomes kind of moot, doesn't it? Flamingo proved it could handle the complex data and generate excellent, validated CoT explanations. The summary Z latent is clearly high fidelity enough given that 92.9% correctness rate. So I think the robustness trade-off is worth it.
Okay. I still remain unconvinced that we should design primarily for the most complex tasks that break the simpler model, especially when that simpler model excels elsewhere. OpenTSLM-SoftPrompt, for me, represents a really accessible, high-performing option for adapting LLMs to the, frankly, very common scenario of shorter burst sensor data activity recognition, sleep monitoring, things like that. Its architectural simplicity gives it a real edge in performance on those tasks.
And for me, OpenTSLM-Flamingo remains the clear winner if the goal is a truly general-purpose time series language model, one that must be able to handle multivariate data, handle extremely long sequences, all without hitting that VRAM wall. Its demonstrated ability to maintain stable memory use while tackling complex medical tasks like ECG QA really establishes it, in my view, as the more robust and forward-looking architecture for general time series reasoning.
Well, I'm still not fully sold that the extra complexity and the fixed overhead of the perceiver resampler and cross-attention are always necessary, particularly when you look at that significant performance lead SoftPrompt has in common constrained tasks like Sleep-CoT. But, stepping back, both these OpenTSLM variants are genuinely groundbreaking. They prove that smaller domain-adapted TSLMs can seriously outperform huge frontier models like GPT-4o on these tasks, and do it much more efficiently, simply by treating time series as a first-class citizen, a native modality.
Agreed. The research here lays a really vital foundation. It moves us towards general TSLMs that can handle all sorts of diverse temporal data. And it strongly suggests that this ability to reason over complex longitudinal information, well, it's going to be hugely important, far beyond just healthcare, anywhere that understanding temporal patterns is key.